Now we get to talk about springs and spring potential energy. Let me find a good spot for my face. Here's a cart oscillating on the end of a spring. Note the energy is all spring potential energy at the 2 points called the end points of the oscillation. So at negative A and positive A. The center of the oscillation is called the equilibrium. That's 0 right here. This is our equilibrium spot. That's where all of the energy is kinetic. So whenever you have motions that are repeating themselves and it's oscillating, it's doing the same thing over and over again. When you're at your equilibrium point, when you're at the center point, that's where your speed is going to be the greatest. So you can see here, we have 0 speed at negative A and 0 speed at positive A, but our maximum kinetic energy happens at 0. So our maximum speed will happen at 0. Same thing would happen with the pendulum, going back and forth. The maximum speed is going to happen when it's at the very bottom. The distance between equilibrium is either endpoint is called the oscillation's amplitude. Amplitude is a distance and given symbol A. You may recall amplitude as being part of a wave, right? This would be the amplitude, how big the wave is. That's okay. If we were to graph this, position versus time, we would get this sinusoidal graph. We would get a sine-like graph. So what you have already learned in your math class is absolutely applicable here. And we'll definitely be dealing with those graphs of motion, because that's what we do. Amplitude is a distance given the symbol A. Note the red arrow on the chart is directly over positive A and negative A the instant the cart stops, and over 0 when the cart goes the fastest. I didn't see any red arrows over here, did you? I see this little pink. That's what we're talking about. Suppose the cart's mass is m, the spring constant is k, and the amplitude of the motion is a. What is the fastest speed the cart attains as it passes through the equilibrium? At equilibrium, all the energy is kinetic, and all of the energy at the starting point is spring potential energy, not force by a spring potential energy. So, our equation becomes the kinetic energy at equilibrium, no gravitational potential energy, or no spring potential energy at equilibrium, equals our kinetic energy at an amplitude at the end point, plus the spring potential energy at the end point. So we have 1/2 mv squared equals 1/2 kx squared. Note that xn equals a, the spring is stretched the same as the amplitude at both ends. There's that substitution. So rather than putting x sub end there, we're just using capital A for amplitude. You may see that in a free response question. Cancel the 1/2 factors and solve for V max. A times the square root k over m. What if the frictionless cart is replaced by a friction-full block? Amplitude decreases as energy is dissipated by the friction. This is called dampened oscillations. In dampened oscillations, something that is interesting is the amplitude is decreasing, so it's getting closer and closer to equilibrium, and eventually it's going to just not move, right? Because there's this external force acting, there's this friction removing energy from the system. You know what's not changing? The time it takes for one full oscillation. One full oscillation, if we're talking circular motion, we would call the period, right? It starts at the top, and then it goes all the way down and around, and it ends up at the top. That's one period. The time that it takes to make that complete revolution is one period. Well, in oscillating motion, you also have a period. And that period is the time it takes to make one complete oscillation. So to go all the way down and then all the way back. whatever time that takes. If you have dampened oscillation, the period is not changing. You're traveling a smaller distance, but you're taking longer time to do it. If you don't believe me, get a stopwatch. Check it out. Note that energy is only lost to friction while the block is moving because only kinetic energy can be dissipated. Vertical springs. So if we've got a vertical spring, suppose the ball has a mass m and the spring constant is k. The ball is released from rest at the end point where the spring is at its natural length. How far below the release point is the equilibrium? The location where speed is the fastest. And we can also figure out how far below the release point is the other end point where the block comes to rest an instant again, where the spring is fully expanded. So we can figure out where our equilibrium is. We can figure out where our amplitude is. Equilibrium occurs when all of the forces balance. Do you see how k times x vector and the mg vector are the same at equilibrium? The kx is the yellow, and the weight equal at the 0. When the ball is above equilibrium, the weight is greater than k times x, and the acceleration is downward because gravity. This means the ball is either moving downward and speeding up or moving upward and slowing down. Do you see how both of these are happening in the animation? Okay. When the ball is below equilibrium, k times x is greater than mg and the acceleration is upward. That means the ball is either moving upward and speeding up or moving downward and slowing down. If kx equals mg, then x equals mg divided by k, solving for x. The distance below the release point, the ball reaches the maximum speed. At the highest point, the energy is all gravitational potential energy, and there is no kinetic energy and no spring potential energy. The spring is at its natural length. At the lowest point, the energy is all spring potential energy, and there is no kinetic energy, and there is no gravitational energy, as long as we call this lowest point our 0. So y equals 0 right here at negative a. We want the length between the release and the lowest point, so we're going to call that L. Then we start with m times g, not times y, but times L, for the gravitational potential energy. And we're going to end with 1/2 k L squared, because we're not using x. So we set the initial energy equal to the final energy. So in the beginning, gravitational potential energy. In the end, spring potential energy. L equals 2 times mg over k. So the distance from the release point to the equilibrium was x equals mg over k, and the distance from the release point to the lowest point was L equals 2 times mg over k. Did you notice how L is twice as big as x? You can see the distance from the highest point to the lowest point is twice as far as the distance from the highest point to equilibrium. So highest to lowest is twice the distance. From highest to equilibrium is just the distance. Logically, that means the equilibrium point is at the center.